Hey everyone, and welcome to This Explainer. Today we're going to untangle a really fundamental concept of computer networking. And you know what? We're going to do it by looking at something most of us have played with since we were kids. Okay, let's dive into this. We are talking about the daily walkie-talkie and how it perfectly explains a foundational networking concept known as half-duplex. So think about this for a second. Have you ever wondered why, whether you're in a movie or just playing around in the backyard, you always have to say over when using a walkie-talkie? Well, it's not just some cool military tradition, it's actually an absolute mechanical necessity. You say over to tell the person on the other end, hey, I'm done transmitting, the invisible airway is now totally clear for you to speak. And in the networking world, computers have to follow very similar invisible traffic rules so they can communicate without just shouting over each other. Here's a quick roadmap for what we're covering today. 1. Half-duplex in daily life. 2. The networking collision problem. 3. Traffic rules with CSMA/CD. 4. Half versus full duplex. And finally, 5. Memory tricks and jokes. Section 1. Half-duplex in daily life. Walkie-talkies versus phone calls. Let's get right into it. Okay, before we can get to the half part, we really need to understand the root word here, which is duplex. Duplex simply defines whether a device can send and receive data at the exact same time. It's basically just the technical term for two-way communication capability. Think of it like a water pipe. Can the water flow in both directions at the exact same time, or just one way? And this brilliantly illustrates our two options. For half-duplex, think of it as walkie-talkie mode. A device can send or receive, but absolutely not both at the same time. If one person holds down the button to talk, well, the other person just has to listen. In networking history, old Ethernet hubs worked exactly like this. But then we have full duplex, which is more like phone call mode. A device can send and receive simultaneously. You can talk, and you can listen to the other person talking over you at the exact same time. Modern Ethernet switches operate this way, which is a total game changer. Section 2. The networking collision problem. The shared mic. Imagine a room. In this room, you have a group of 5 energetic people. Now imagine giving those 5 people exactly one shared microphone. What happens if 2 people get super excited and try to speak into that single microphone at the exact same moment? You guessed it. Nobody can understand a word either of them is saying. It just becomes chaotic, jumbled noise. And this is precisely what happens in old half-duplex Ethernet networks, where a bunch of devices share the exact same physical cable. Boom, you get a collision. When 2 computers try to talk simultaneously on shared network media, like one of those old hubs, their electrical signals literally physically crash into each other on the wire. The data just becomes totally corrupted and completely useless. It is a literal traffic accident on the information superhighway. Because of this chaos, networks desperately needed a traffic cop. They needed some ground rules. Section 3. Traffic rules with CSMA/CD, bringing order to chaos. All right, here's a massive, intimidating acronym for you. CSMA/CD. It stands for Carrier Sense Multiple Access with Collision Detection. Now, I know it sounds like absolute alphabet soup, but I promise it is incredibly logical when you break it down piece by piece. It is literally just the step-by-step traffic rule for shared cables. It teaches computers how to be polite and wait their turn, exactly like you would on a daily walkie-talkie channel. Let's actually walk through exactly how a computer, let's call it PCA, uses this rule. Step 1 is carrier sense. PCA literally listens to the wire first to see if anyone else is transmitting. If the wire is busy, it waits. If it's quiet, it moves right along to step 2 and 3. Multiple access just means everyone is sharing this wire, but since it's quiet right now, PCA can transmit its data. Now, step 4 is absolutely crucial, collision detection. Even while PCA is sending its data, it keeps one ear open, listening. Because what if PCB on the other side of the building started transmitting at the exact same millisecond? If they crash, both devices detect the collision. That triggers step 5, the jam signal. Both devices instantly yell stop, a collision happened, over the network so everyone knows the data is totally corrupted. Finally, step 6, and this is the brilliant part, random back off. Think about when you and a friend accidentally start talking at the exact same time on a phone call. You both stop, wait a random split second, and then one of you starts again, right? Computers do the exact same thing. To prevent crashing into each other again, PCA might randomly wait 2 milliseconds, while PCB randomly waits 5 milliseconds. The one with the shorter wait time gets to go first on the retry. It is just an incredibly elegant solution to that half-duplex chaos. Section 4. Half versus full duplex, the direct comparison. Let's move to a direct comparison and see how this builds. in a direct comparison and see how this builds. In a half-duplex setup, because you cannot send and receive together, collisions are absolutely possible. This means those complex CSMA/CD rules are completely necessary. This was the era of the old network hub, where all the bandwidth had to be shared. But now, look at full duplex. Can you send and receive together? Yes. Are collisions possible? No way, because every single device gets its own dedicated sending and receiving path. So, is CSMA/CD needed? Nope, not at all. It's completely disabled. This is the era of the modern switch, where bandwidth is entirely dedicated to each specific link, not shared with everyone else. So, the absolutely crucial point here is understanding when these rules actually apply. Let's test this out with a classic, easy exam question you might actually see if you were studying for an IT certification. Ready? A PC is connected to a modern switch using full duplex. Is CSMA/CD used? Think about it for just a second. And the answer is definitively no. It's a bit of a trick question, to be honest, because it tests your core understanding. If you are on a dedicated full duplex switch connection, it is physically impossible to have a collision. You have your very own lane for sending and your own separate lane for receiving. No collisions mean you absolutely do not need the collision detection rules. It's that simple. Section 5, Memory Tricks and Jokes, Making It Stick. Here is a brilliant little memory shortcut to keep the eras of networking straight in your head forever. First, remember the 3 H's. If you see a hub, it operates in half duplex, and therefore collisions happen. Hub, half, happens. Conversely, remember the SFN rule for modern networks. Switch, full duplex, no collision. SFN. If you can just anchor those simple acronyms in your mind, you will instantly understand the underlying mechanics of pretty much any local network you are looking at. Let's give a little personality to our hardware to wrap this up. Why doesn't CSMA/CD work in full duplex? Well, because the modern switch looked at all the computers and basically said, look, everyone gets their own lane, no fighting, no collisions, no drama. Meanwhile, the poor, exhausted old hub over in the corner is practically begging the users, saying, sorry folks, one cable, one microphone, please borrow patience, not bandwidth. So by understanding how a simple daily walkie-talkie works, you now understand the foundational history of data transmission and half-duplex. But as you know, networking is a massive, incredibly interconnected topic. So I'm going to leave you with this final thought. Want to see collision domains versus broadcast domains explained with real-world cartoons next? Keep that curiosity alive, keep exploring, and I will catch you on the next explainer.